Hello again everyone, welcome back to ptet.chemistry channel. This is the 8 of 10 video series on these infographics that have been provided by Cambridge International Education during the pandemic period on their Resource Plus website. If you want a copy of this PDF of these infographics, I put it down on the Google Drive link in the video description below. That's if you want a copy of it, I guess. If you are looking for a video tutorial on A-level chemistry, this is not the right video for you. What this video is about is topic connections regarding to controlling reactions. This is the second one. I think in the earlier part of this video series, there's one video that's on controlling reactions 1. That's on the more basic stuff, whereas here we'll be talking more on the energetics, which is on thermodynamics. And we'll be talking a little bit about rate of reaction, which is reaction kinetics, and how you cannot confuse between thermodynamics and kinetics, as they are the type of questions that even examiners have liked to ask since O-level GCSE. That's called rate versus equilibrium. They mix in the rate and equilibrium type of questions together. Yeah. So if you're looking for those tutorials, feel free to just leave this video and browse through the topical playlist for the rest of the A-level topics in the remaining part of the channel, I guess. So just browse around and see what topics that you need help on. Just bear in mind that what I've labeled as AS or A2 might have been different for you, because it depends on your specification. But the whole idea of having them in sorted out in topics is so that whatever specification you're doing, the contents within will be relevant to you regardless. Okay, as a 16 to 18 years old chemistry learners. So in this video, they start off by talking about enthalpy change, which is an AS concept in our Cambridge International syllabus. You're expected to know formation, combustion, atomization, hydration, and solution. So these are all standard definitions which you need to know how to define, but I find it best if you know how to define them by going through examples of equations. That's why you can find in my topical playlist on AS energetics, I go through examples, I go through equations after the definitions, and you can see through work examples of how these concepts are being combined together in one whole big unifying concept as I go through questions. We talk about the strength of the ionic bond as an indication of lattice enthalpy, because there's another definition that is in A2 chemistry. Okay, even though they put it under 5.1 enthalpy change, but lattice enthalpy is covered in A2 energetics, and you can find in the A2 energetics topical playlist where we discuss a lot more on this, and we combine to Born-Haber cycle. Okay, so obviously that affects that is an indication of the strength of the ionic bond. They become more exothermic. Okay, so become more and more negative. We talk about the magnitude or the value increases as the ionic bonds get stronger due to bigger ionic charges, highly charged cations, and also smaller ionic radius, because as you know, atomic radius decrease down that way, ionic radius decrease down that way. So there's Na plus, that is Al3 plus. Atomic radius, ionic radius, part of your atomic structure topic. You can find out more from the atomic structure playlist for A-level chemistry. Okay, I think I talked about it in the other video that is on part 7 about the relationship to atomic structure, where you need to work out nuclear charge. There's still the protons in the nucleus. When you think about how shielding changes across a period as well as down the group, and of course the overall effective nuclear charge, which takes into account nuclear charge and the shielding, and that can affect your ionization energy, electron affinity, that can affect electronegativity, and that can affect atomic and ionic radii. Okay, so those are all important stuff. This is just an example of an equation to show first electron affinity, but that equation is very bad because the definition is incomplete without the stat symbol. As you would know, even from writing the first ionization energy equation, without writing the stat symbol, it does not mean a thing, because the gaseous, from 1 mole of gaseous atom gaining 1 mole of electrons to form 1 mole of gaseous anion or gaseous ion with single negative charge. That's the full complete definition, so do not forget that. We'll talk about the use of Hess law, whether we incorporate in formation or the other one is incorporating in combustion. When do we use the formation of product minus formation of reactant? When do we use the combustion of reactant minus the combustion of product? So I mean, there are two different kind of situation, and you have to learn when to use one or the other. So there's the formation of reactant, whereas the other one is combustion, the combustion of reactant minus the combustion of product. And of course the other one is to do with bond energy, bond dissociation energy broken minus bond dissociation energy formed. There's another one which I haven't shown here. There's to do with calorimetry. Okay, so by, let's say, combustion of a fuel, you will have the opposite sign. Okay, and then the MC delta T, okay, over the mole of the limiting reactant, where your delta T has to be final temperature minus initial temperature. Put a negative because this is the surrounding. This is what happened to the water. The negative is because the system, if the water heats up, if the solution heats up, then your enthalpy change is going to be negative because your reaction is exothermic. It released energy to the surrounding, which is the water, which is the solution. If your final temperature is lower than your initial temperature, then delta T will be positive. It will be negative because TF is lower than TI. That's because your water or solution gets cooler because the reaction is endothermic. Minus minus will become plus because your is endothermic. It will absorb energy from your surrounding, from your water, from your solution. Okay, you can find out more about applications, when to use what, by seeing how I work through examples in the tutorial playlist on AS energetics. Okay, this is an example of how in a Born-Haber cycle we relate formation, lattice enthalpy, ionization energy, electron affinity for the anions, as well as the atomization. All of these have to be accompanied by stat symbol, just like that, because without stat symbol, they will not have the same meaning or definitions. Okay. In the other video, I think in video 7 of this infographic series, we saw this group 2, I think it's video 6 or video 7, I'm not entirely sure, but we have seen this group 2 chemistry under periodicity. In AS, you are expected to just state the thermal stability as well as the solubility trend, but it's very, very important to be able to prepare in a paper for A2 theory paper, to prepare for how to account for the thermal stability of the carbonates and nitrates, how to account for the solubility of the hydroxide and the sulfate completely by talking about this thing that involve different concept, this thing that involve entirely different concept, but it comes down to the ionic radius, okay, the number of shells, and we talk about the charge density, the charge density of the cation, the charge density of the cation. So you might think that they are the same, and that's why students always get confused. Up until that point, they are the same, but what is different? What is different then is, this will be talking about polarizing power of your cation, okay, on the anion, which in this case is CO32 minus, and in this case is NO3 minus. So you need to talk about on the CO32 minus or NO3 minus, and then we talk about is it easier to break the CO bond? is it easier to break the NO bond going down the group based on this, based on this. On the other hand, how is this one different? Okay, this is to do with solubility of hydroxide and the sulfate. We need to talk about lattice. Okay, lattice enthalpy. We need to talk about hydration of the cation. Hydration enthalpy is not a new concept. It is a AS related concept. What are the factors that affect hydration enthalpy? What are the factors that affect lattice enthalpy? Okay, and then both of these combined, you will get enthalpy of solution. Okay, if it become more soluble, down the group become more soluble, the enthalpy of solution will become more exothermic or less endothermic, and vice versa for the sulfate, which follows opposite trend. These are all covered in my topical playlist on A2 Group 2 Chemistry playlist. So make sure you find out how I explain the solubility trends as well as the thermal stability trends. Yeah, being able to tell a story on your own is going to help you in the long run. Okay. This bit is about entropy and is covered in A2 playlist under A2 energetics. We talk about increasing disorder as a result of increasing entropy, because entropy is a measure of disorder or randomness in a system. A gas will have higher entropy than liquid, that's solid. We also talk about counting the number of molecules. That means in a balanced equation, you count the number of moles in front. There's the number of molecules, number of reacting particles, in addition to seeing whether it's solid, liquid, or gas, and knowing that entropy of gas is so much bigger than entropy of liquid, than entropy of solid. Okay? And then we relate that to this feasibility. They call it feasibility, but you can also call it spontaneity. Is the reaction spontaneous? Is the reaction feasible? Okay. So these are just how do I say this? These are just generic representations, but this is the completely important equation. Students always forget that delta G and delta H is usually presented in kilojoule per mole, and delta S is usually presented in joule per mole per Kelvin. So when you combine delta S into this equation, you have to divide your value by 1000 if you have this unit in particular. Okay, if you wish to work in this unit, you have to work out the delta G and delta H by multiplying by 1000 to convert them to joule per mole. Okay, and when delta G is negative, it is feasible and spontaneous. Okay, and you can work out this sign by working out the individual sign of delta H and delta S. Take note that this is minus T, so minus T times minus delta S will give you positive. Alright. Another thing is temperature is in Kelvin. So they like to give you the temperature in degrees Celsius, and if you forget to convert to Kelvin, you get the wrong answer. You also need to take note that equilibrium, or the temperature at which the reaction will become feasible, if it is originally not feasible, is when you set delta G is equal to 0. That means delta H minus T delta S equal to 0. T is going to be delta H over delta S. This is a common mistake again. I mean, rearranging the equation is okay. A common mistake here will be forgetting that the unit and the unit must be the same. Only then, you see kilojoule and joule, they are not the same. When you put them in like that, they are not going to cancel out the unit. You want the unit to be in Kelvin to get the temperature. Alright? Rate versus equilibrium. I think it was well covered in controlling reactions 1. But in case you forget about that, we talk about rate versus equilibrium. I'm sure you know all about that from your AS chemistry, even O level. They love to combine when the temperature increase, is the reaction faster or not? Explain. There's collision theory and Maxwell-Boltzmann distribution theory. When you have a reaction which is also in equilibrium, such as Haber process or the contact process, the formation of NH3 or the formation of SO3, okay, when the temperature increase, will you get more product? That is a very important question, and people thought just because reaction is faster, you get more product. But remember here, if you are in equilibrium, you have to consider Le Chatelier principle. Thermodynamics and kinetics, they are not the same, and that is what they love to confuse students, okay, in exams question. In A2 rate of reaction, you can find out more about calculations, working out whether it's zero order, first order, second order, working out rate determining step, suggesting mechanism. So I would advise you to go through the examples, because going through the theory is not going to help you very much unless you know how to apply it in example, and unless you know also that rate of reaction topic, it's very often asked not just in paper 4 but also in paper 3 setting, because it involves experimentation, it involves plotting graph, it involves analysis and interpretation of result. That's why it's also very popular in paper 5 as part of design and analysis kind of question, but also interpreting results. Okay, the other result of course is to do with the Arrhenius equation, which you don't specifically do in CIE Cambridge International syllabus, but you must have seen this in a practical setting where they ask you to plot this result, or even in a paper 5 setting where they ask you to interpret the result. So y equal to mx plus c is a straight line graph now. You plot that, where rate is inversely proportional to the time taken for the reaction. This is your y-intercept. You can work out A, which involves the collision theory. Okay, the collision theory, you know, talking about how often the reacting particles will collide. That is actually termed the pre-exponential constant. Don't ask me how they come up with that term, but it's an idea based on collision theory. This thing is based on the Maxwell-Boltzmann distribution, which is to do with activation energy. As you remember, Maxwell-Boltzmann distribution is to do with the number of particles with energy E. This is energy on the x-axis, okay, and we talk about at higher temperature. At higher temperature, you have more molecules that have higher energy than EA to react. Okay, but yeah, I mean, we're closing towards the end now. So rate constant to temperature. What am I gonna say here? I forgot what was I gonna say already. I forgot, sorry, my mistake. This is not rate, it is rate constant, if I'm not mistaken. Rate constant, yep, there's rate constant. Okay, there's rate constant, and then rate is proportional to K, because K is present in the rate equation. You see, K, which is rate constant, is proportional to rate, and rate is proportional to 1 over time. Therefore, K is proportional to 1 over time. Okay, that is how you get that. My bad, that is actually rate constant. So rate constant will increase with temperature when you have positive activation energy, which is true for like 95-97% of chemical reaction you will ever encounter in your life. Okay, constant activation energy, reaction rate, rate constant, Maxwell-Boltzmann distribution. They're left to combine with thermodynamics, especially when you have an equilibrium type of question. And yeah, it's just all to confuse students to see whether you get the concept or not. So there's quite a lot of relation between thermodynamics and rate, but also not a lot of relations. It's just that they are connected and they love to be linked together in terms of what we perceive as controlling reactions. This is the end of this short videos on connecting topics, and by no means is an overview of your syllabus, so always refer back to your specification and what you need to cover exactly. Check out the rest of the topical playlist on A-level topics, not just AS topic but also on A-level topics on my channel. So browse through the whole channel and you will see the full range of topics available. Please share them with your students if you are a teacher. Share them with your classmates and friends and class group chat and relative if you find any of the videos and the content on my channel useful for them. Thank you for watching.